Hi, we are from Group A, and this is our video on our grass cutter design and analysis. So, for your introduction, University Malaysia Sarawak Unimas maintains one of Borneo's largest academic campus, spanning 1,040 hectares of diverse terrain, including rainforest buffers, sport complex, and urban landscapes. This project responds to Unimas' commitment to occupational safety and sustainability by redesigning grass cutting equipment for campus-specific needs. So moving on to our problem statement, our agricultural workers often face physical strain and health issues due to prolonged use of traditional grass cutting tools. These tools are typically heavy, inefficient, and require long hours of operation under harsh environmental conditions. So common complaints include back and arm pain, hand tremors, and fatigue from extended exposure to the sun. There is a need for a lightweight, ergonomic, and efficient grass cutter that can reduce physical stress and improve productivity. So the objective of this project is to design and analyze a lightweight, ergonomic, and battery-powered grass cutter that reduces worker fatigue, enhance cutting efficiency, and adheres to international safety and ergonomic standards. The design should be simple, cost-effective, and suitable for large area coverage. Following the standards, our grass cutter design follows four key standards: ergonomics to reduce injury risk, efficiency for large area coverage, and safety with dual switch and blade shield, and sustainability using battery power, all based on ISO and UNIMA standards. So our design focus on safety, ergonomics, and technology. Key features include a dual control switch, cutting shield, adjustable handle and shaft, a foldable body for storage, and a 650-watt motor powered by a lithium battery for efficient cordless operation. So as you can see, uh, our final design is shown here. So our grass cutter supports three sustainable development goals, which is SDG 3, SDG 8, and SDG 13. For SDG 3, our design have a vibration dampening. SDG 8, our design have an ergonomic design, and SDG 13, our design have zero operational emissions.
Hi everyone, my name is Muhammad Razia Amin bin Zaidi with metric number 82749 from Group A. For this session, I'm covering the analytical calculation of the stress and deformation experienced by our blade. We assume the blade behaves like a cantilever beam, fixed at the center and extending outward. The material is aluminum alloy with a Young's modulus of 70 GPa and a yield strength of 300 MPa. The blade experiences both centrifugal body loads and pressure during operation. Our goal is to validate its mechanical strength before we move on to simulation. The objective of this experiment is to calculate theoretical maximum stress and deformation experienced by the rotary blade under a pressure load of 25 MPa and gravitational force. We first calculated the moment of inertia using the blade's cross-section that applied a pressure load of 25 MPa to estimate total force. This gave us a bending moment of 20,000 Newton meter, which led to an estimated bending stress of 333 MPa, far above the material limit. So we reversed the calculation using the observed 6.8 MPa from our report. That gave us corrected moment of 0.408 Newton meter and a force of just 4.08 Newton, which better matches realistic condition during cutting. Using this revised force, we calculated tip deflection using the formula in the slide, and the result was 0.32 millimeter, exactly what we observed in simulation. This proves our analytical model aligns with the simulation output. In summary, the blade operates far below yield strength, deflects only slightly, and maintains structural integrity under load. These results give us great confidence in the safety and reliability of our design. That's it for me. Thank you.
For the software simulation, we're gonna use the Autodesk Inventor Professional 2019 stress analysis report. Then we're gonna set the constraint to the center hole to simulate the hole being rigidly connected to the motor shaft where all the translational and rotational degrees of freedom are restricted. We also put a pin constraint to simulate free rotation along the axis of the motor shaft. Then for applied force, we're gonna use the body load to approximate its centrifugal force. Therefore, we gonna use the angular velocity of 60,000 degrees per second. And here is the simulation results of the analysis report. As you can see from the 1 meter stress, the maximum stress experienced by the blade is at the edges of the blade nearing the center with maximum stress of 79 megapascal. Then for displacement, the maximum displacement of the blade is at the end of the blades at 0.025 millimeters. And for safety factors, we can say that the blade will not experience any failure as its minimum safety factors is at 3.
The differences between analytical and simulation results was minimal, with less than 5% deviations. This validates the accuracy of the theoretical model and confirms the reliability of the simulation setup. Sources of error, including boundary condition assumption, mass resolution, and material property approximation. The analysis results demonstrate that the blade design is structurally sound and capable of withstanding operational stress. The use of aluminum alloy ensures a balance between strength and weight. Minimal deformation confirms that the blade's durability and safety. The safety factor of 2.5 supports the reliability of the designs. Its findings validate that the feasibility of the final designs and its suitability for economic and efficiency cross cutting. Design decisions such as material selections and the blade geometry were influenced by this result.